Hey guys, welcome. Yeah, so example 5 here, and we want to know the largest cylinder that we can put in a sphere of radius 6. And so this is a really cool question, and yeah, so what we're trying to maximize is the volume of the cylinder, since we want the largest cylinder, right? And our constraint is clearly like having to be bound by the sphere, right? So let me draw a couple of important visuals. So first of all, if I went all the way here, notice I just uh, drew something that's of length 6, because I just drew the radius of the sphere. But if I had not gone all the way and instead went from here to here, then I just drew the radius of either the top or bottom circular end caps of our cylinder, right? And so this is important, what I just drew, and it's a right angle right there. Okay, and yeah. So this is 6 here, right? And let's start writing what we know. So first, what we need to minimize or maximize is the volume of this cylinder, and what we want is like actually maximize. So we want V is equal to pi r squared h, right? So that's the volume of the cylinder, and that's what we need to maximize. And again, we need this V to be all in terms of one variable. And what's going to help us do that is some sort of constraint. And what is our constraint? Well, see, if you look at this triangle that I've drawn right here, that's what's going to bound us so that this distance right here, the hypotenuse of the triangle, is 6, meaning it's fixed by the radius of the sphere. So that's what's constraining us, the fact that this has to be 6, right? And this little guy here is r, the radius r here of the cylinder. And this distance here, the other leg of the right triangle, is h over 2. Notice it's half of the height of the cylinder. So what we have, based on this triangle right here, is that, and if I write it in green, our constraint function is little r squared, where little r is the radius of the cylinder's either top or bottom end cap, the circular end caps. Yeah, little r squared plus h divided by 2 squared will have to equal 36. And that's our constraint, right? Okay, cool. And our constraint function, remember, is what's going to get us to write a volume function that's all in terms of one variable. So perhaps we should simplify our constraint function a little bit more. So we can write r squared plus h squared over 4 is equal to 36, right? And from that, clearly, we could either solve for h squared or solve for h in turn, or solve for r squared. It looks like the easiest thing to do is to solve for r squared. And so let's do that. R squared. Sorry, I didn't like that r. R squared is going to equal 36 minus h squared. H squared over 4. And so then we can take this r squared, which is 36 minus h squared over 4, and substitute for this r squared. That way our volume V of the cylinder is all in terms of one variable, namely h. So we can write V of h, right, is equal to pi times r squared is 36 minus h squared over 4, and then times h, right? Okay, cool. We could write that a bit simplified, or at least easier to take the derivative of, as 36 pi h, and then minus pi over 4 times h cubed, right? That's right. And this again is v of h. And what we need to do is take the derivative. So v prime of h is going to equal 36 pi 36 pi, and then minus, it's going to be 3 pi over 4 h squared. Right? Okay, and we need to set this equal to 0. So, say equals 0. And that will imply that we've got this, which is that we need 36 pi to equal 3 pi over 4 times h squared. Okay, where to from here? Well, we need room. So how about we do this? How about we take this and put it right there? And how about we get rid of this? And then slide this up. And what are we gonna have? We gonna have, well, from here, what could I do? Well, I could get rid of that pi and get rid of that pi and get rid of this 3 and turn that to a 12. And so I have 12 is equal to h squared over 4. I can multiply both sides by 4 and write that h squared is equal to 4 times 12, I believe, is 48. Okay, cool. And that's 16 times 3, right? So h is going to equal 4 times root 3, right? Okay, cool. H is equal to 4 times root 3. What else do we have to solve for? We have to solve for r, right? So find the dimensions. Yeah, how would you solve for r? I don't know. Like, you'd use this equation right here. So h squared is 48. So that'd mean that r squared, which is equal to 36 minus h squared over 4, would be 36 minus h squared is 48. So 48 over 4. 48 over 4, I believe, is 12. So r squared is equal to 12, which means r is equal to the square root of 4 times 3. So that's 2 root 3. So r is equal to 2 root 3, and h is equal to 4 root 3. And that is how we're going to maximize the volume of this cylinder that is contained in a sphere of radius 6. Now, yeah, so this h and this r clearly are the dimensions of the cylinder, and we are done here. Yeah? All right, cool. Like I said, there might be a couple of bonus examples after example 5, but otherwise I hope examples 0 through 5 have served you well. And keep watching, and yeah, take care.